Hi boys and girls, welcome to a new IB Physics video. In this video, we'll talk about X.1 energy resources. Bear in mind that this is a self-study unit, so you should have read the textbook already before you start doing the homework and check the solution. As usual, let's have a look at the study guide from IBO. I think the most important thing that you could see here is understand the term for specific energy, and also energy density, and also how to read the Sankey diagram. And after that, you should know there are many kinds of energy resources and how they work. And also you may want to pay attention to the data booklet here. They have given you two equations. However, these might not be the only two equations that you use. In this chapter, I will do a few more recap from the textbook in case you may not fully notice what are the focus in the textbook. So the first thing is about the specific energy and also energy density. As you can see from the definition here, specific energy is the energy per unit of mass, and while energy density is the energy per unit of volume. So I think the way to memorize it is actually very easy. For specific energy, you can recall specific heat capacity, which is how much energy you need to increase one temperature, 1 degree Celsius or Kelvin per 1 unit mass, right? So it's the word specific here is talking about the mass. And while density, energy density is very obvious, can be referred to density itself, mass over volume. So how much per volume you have. So that's why you divide by volume for energy. And also you may have a look of the work example here to look at how you can mathematically express these two. Next up, I want to show you two tables from the textbook. Although these are not really relevant to your exam, but I think it's very good to know. The first one is about the uranium, which you may, of course, you know is for nuclear power. And you can see that is very sensible that it has a very high specific energy and also high energy density as well. That means for a small volume or small mass of uranium, it can produce a lot of energy in a nuclear plant. Maybe you can also look at hydrogen as well. Relatively speaking, it has a higher specific energy than the rest of the more common fuel. And this is also one reason why people are trying to invent hydrogen car. So that means using hydrogen to power the car, apart from electricity like the Tesla. For the table here, it took me a few seconds to understand what it means. In fact, what this table is talking about here is a total of 100%. So that means this is the total energy production of the whole world. So you can see that the main three fuel that we use is oil, natural gas, and coal. Especially the oil. However, these main three fuel will produce a lot of carbon dioxide respectively, while nuclear, hydroelectric, biofuel, and others may not bring you any carbon dioxide or very insignificant amounts of carbon dioxide. So you can imagine that as you all are young scientists, right? So in the future, if our government policy and the world policy can steer our way apart from using all this energy into maybe using the renewable energy or nuclear energy, then we can reduce a lot of carbon dioxide in that case. Sankey diagram. Pretty sure you have seen it in IGCSE, but the one that you have seen before is not in plotted scale. So what you can see here is the grid here represents the amount of energy. So say here you got 10 grid, and here you got 2, so that's why it's 20. Here you got 4, so that's why it's 40. And you can see after 2 went down here, and you have 8 grid, which means 80 units of energy keep going. And then here you can see the process. Another thing that you can see from this Sankey diagram is those arrow going downward is supposedly those energy which are wasted, and while only the one keep going forward is the so-called useful energy. Next up, you should, while you are looking at the question, especially the example, although some of them you may find a bit unfamiliar, and also there's no really specific formula for those questions, but always try to look at the unit. Let's say here, what you could see is here is 245 watts per meter square, and then blah blah blah, the efficiency is 20%. Estimate the area which can provide you this. So basically you can see that this is the power over A, and this is the power. So if you want to find area, then I think it's pretty obvious in that case. So this is how you can look at the unit and figure out the relationship between the variable. Next is about the hydroelectric power. In the data booklet, there is no this equation provided. So well, we never know whether or not it will be assessed in the actual exam. So make sure you know how to derive this equation, and it's actually pretty easy if you look at that. So basically, you need to know that this is a P is the power, and power equal energy over time, right? So mgh is the GPE that you have at the top here, while well, T is the time difference. And then what you can do is you change the mass into density times volume. I think it's pretty easy. And then after that, you can reallocate this equation with the delta V over T. That means the volume per second. So in that case, this is so-called the flow rate according to the textbook. So you may derive this equation, or it really depends on the situation, that like what data you have, then you can derive it. But the main thing is GPE over time. Next is the pump storage system. I don't think it appeared at all in any IGCSE physics textbook. So the main idea is actually very simple. So well, as you can read from the textbook, that is during the off-peak hours. That means the demand of electricity is very low, while you may still probably generate a lot of electricity. So in that case, you want to store them, and then whenever later on, when you get into the peak hour, you can use it again. So what they do is after they got the electricity, they use a pump to pump it up to an upper reservoir, and then when they need the energy, they need the electricity, then they will release the valve here and then let the water flow down again and get the electricity. So this is the idea itself, but pay attention that there's no 100% efficiency system in the world. So in that case, you may not always want to do it, because in that way you usually lose some energy in the process, while those energy will transfer to the waste energy. Wind power, the equation is already provided from the data booklet, but I think it's still great if you can look at how we can derive it. So simply is that the kinetic energy is what you learn 1 over 2 mv squared. However, for the m here is very different from how you do in talking about a solid, right? So the mass here is calculated by density times cross-section area. That means the like the circle here, and then times V times delta T. So in that case, you can find basically the volume of this cylinder times the density here, and then it will be the mass of that specific amount of air that you're talking about. So in that case, you can derive the equation you see in the data booklet. Nuclear fission. If you look at the textbook, you can see the structure of the nuclear fission, and especially the control rod that in every nuclear plant they will have. And also you can look at the uranium atoms inside, and I would I would really encourage you to try this website, and I mean this simulation. And basically, if you try it after you read the textbook and you try it, you understand what it means by the control rod. When you are doing the textbook exercise, you may come across this unit EV, and if you check the Wikipedia, then you can find out 1 electron volt is equal to 1.6 something times 10 to the power negative 19 joules. So how are you going to know this? And you can find out that it's actually not in the data booklet as well. Let me tell you a trick. You need to recall what you learned in IGCSE electricity, that voltage is equal to energy over charge in coulomb. So in that case, if you know 1 electron, which is can be found in the data booklet, that 1 electron equal to 1.6 times 10 to the negative 19 coulomb, then you can basically find out how much it is for 1 electron. In case you don't know what it means by coulomb, then you can think about this. 1,000 is something like mole as well. 1,000 is like 12, right? Well, let's say when you're applying flowers, right? 12 flowers. So in that case, you may also say 1 flower is equal to 1 over 12,000 as well. So here is the idea of how you count the stuff. But anyway, for 1 EV, it's very obvious that you use E times V, right? So here you got 1 electron, so 1.6 times 10 to the power negative 19 coulomb. And then if you times V, which is, you can see E over Q, then 1V. Then eventually you can find 1.6 times 10 to the power 19 joules in that case. So this is how you can find the unit EV and convert them into something sensible to you. Alright, last one. I want to show you the data booklets again. This is annotated by student that I already upload on ManageBack. You may find it. So you can see once again, you only got 2 equations. So I'm not entirely sure about whether or not you will need the equation for the hydroelectric, but yeah, just keep that in mind that these are what you learn. Question 1A, basic definition you can find from the textbook. For B is what I said, you start with the basic definition, density, right? So divide by V, and then energy will be mgh, and then you can derive it by yourself. Question 2 is very easy. I think you can read it by yourself. For 3A, basically you can see it said for each day it has efficiency of 80, 40, 12, and 65. So what you do is you times them together. I think you learn it in something similar in maths. So at last you will get 2.5% if you express it in percentage. For the Sankey diagram, you can see that every time in other words, you wasted 1 minus the efficiency. So like the first one, 1 minus 80%, so 20 is wasted. And after that, going on 80, out of 80 you got 1 minus 40 wasted, so 48. And then 48, 80 minus 48, then you got 32, and then so on and so forth. And therefore you can draw this diagram. 4A, it's a very simple question, just to pay attention to the unit itself. Let's look at the question. It's at 30% of efficiency, and then you burn 10 million kilogram of a coal a day, and then take the specific energy to be this. And then part A is to calculate the power output. So what you do is you take the specific energy. Remember, it's to times kg. If you are not so familiar, I would recommend you put down the unit like what I did here. And then for calculating the power, then you need to put down you need to times the kg, which is the mass here, so 10 times 10 to the power 6, which is million. And since it's a day, and therefore you need to over 60 times 24 for calculating 1 second. And then since the efficiency is 30, so times 30, and then last you can you should be able to find this answer. For part B, it estimates a rate where the thermal energy is being discarded by this plant. So in that case, one thing that you need to know is 30% is the useful power output, right? And therefore 70% is the wasted energy. So what you do is you use simply use the useful one, which I find in part A, divided by 0.3, which you can find the original power, and then you times 0.7, then you should be able to find the answer, which are wasted. For part C, it's a very interesting question. If you look at the question, it said the thermal energy is carried away by the water, which temperature are not allowed to increase by more than 5 degrees Celsius, and calculate the rate where the water must flow. So in that case, you need to think about the water is absorbing the thermal energy in the rate of 2.4 times 10 to the power 9 watts. That means joules per second. And therefore, you can think about in 1 second, then you will have 2.4 times 10 to the power 9. And then this energy will be absorbed by calculating mc delta T, what you learn in thermal. So mc delta T over time. So if you are asked to calculate the flow rate, then it will be mass over T, because it's talking about how much mass per second, right? And therefore you can find the rest by putting C and delta T on the other side, which is over 2005, and you can find the answer is 1.1 times 10 to the power 5 kg per second. So pay very close attention to the unit, will be extremely helpful. Question 5, these are the keywords that I assume you should have highlighted. So what they want you to do is calculate how many kilometers the car can go with 1 liter of gasoline. It's a very interesting and practical question actually. So you can imagine that the speed of the car, 9 meters per second, is in terms of energy is KE, right? And while it says the power developed by the engine, 20 kW, is actually used for work done against friction or air resistance, because think about the car, in every second it takes 20 kJ in 1 second. So this is used against the friction or air resistance in terms of work done. It's not for KE. Think about the car is keeping the same speed, and therefore it's not for KE at all. So this is very important. By calculating the useful energy output by 1 liter, you look at the original information, 34 megajoules. So 34 megajoules times efficiency. So this is the useful energy. And since you are talking about the power is given as 20 kilo, then you just basically write the energy over time in that case. Then what it means is for 1 liter of gasoline, you got that much of energy, and it can take you for against the friction air resistance for 680 seconds. And therefore the distance travel will be 9 meters per second times the second times the time. Therefore you can find the distance. You may wonder why, then why do we there's no need to calculate the KE. Here is basically one thing is you don't know the mass of the car. Second thing is you may assume the car is already moving, so it's not starting from the rest. Question 6 is a bit similar to the previous one. I think you can read it by yourself. Question 7, and these are the model answer from the textbook, and I highlighted the keywords, and well, I suppose you have already read the textbook and it should not be a big problem for you. Yeah, so I think you can read it yourself, and make sure you got the keywords that I highlighted below. For question 8 is something that not really taught in chapter 8 here. Instead, it should be from chapter 7. So that's why they expect you to know this. However, the order that we do is a bit different. But anyway, I think it's a good practice for you as well. Maybe you can follow my video here and then see how you can do it. So basically, this is a nuclear fission reaction. This is uranium, and this is also uranium, but they have different atomic mass, and then they would split into smaller atoms. And these are the mass data, which later on in your calculation you can calculate the change of mass, the mass difference. So simply you just look at before and after what happened. And then you can find, in fact, the mass has a very small difference. And according to the data booklet, for the mass here is actually can be times this number, which is 931.5 mega eV, and you can convert it into the energy. And this is in fact what people talk the most about Einstein, the very famous equation E equal mc squared. You can find in your textbook in chapter 2.7.2 page 285 more about that. Basically is talking about you convert the energy into mass. So this is a very shocking, surprising result developed by Einstein, that in the past people do not know that, oh, mass is mass, energy is energy, but they never thought of the fact that energy and mass, they can interchange with each other. So that's why Einstein theories makes the nuclear power work and also the fission reaction work. But well, anyway, we'll talk about more about this in chapter 7. For part B, what it said is the whole power plant output is 200 megawatts. So from part A, what you calculated is 185 mega eV. This is talking about one atom only, as you can see from the reaction here, one uranium atom only. And therefore, if you're talking about n numbers of uranium atom taking the reaction, therefore with n times 1x5, and then if you convert it to joules, then you have to times this number mega, and then this is eV, if you remember that, and then equal to the power output, which is 210 to the power 6, and therefore you can find the answer, which is having 2.x times 10 to the power 18 numbers of atoms reacting in each second. Part 9a. Part A asks you to calculate the specific energy, right? So as you remember, specific energy is talking about the energy per kg. So 1 kg. 1 kg over 235 gram, because that is the molar mass for uranium, and therefore you can calculate for 1 kg it has 4.26 moles, and therefore you can find the numbers of uranium is 2.57 times 10 to the power 24 if you times the Avogadro number, and then you can finally calculate the numbers of atoms times for each uranium, and you may find the total energy released will be in this 5.14 times 10 to the power 26 in m mega eV per kg, and therefore if you convert it to joules, then it will be x times 10 to the power 13 joules per kg. So it's all about the unit. For part B, estimate how much coal must be burned in order to give the same amount of energy as released with 1 kg. That means what you calculated in part A. So you may write E, which is the same energy, for what you do above. This is from part A, and then 30 megajoules per kg. That is the specific energy, and then times m, and then very simply you can find by algebra the answer. Question 10 is also similar to the previous question, so please read it yourself. Question 11. I did not expect they ask you to draw. I mean, in the actual IB exam, I don't think they will ask you really, draw from scratch of a fission reactor. But the main thing is already highlighted below. You can have a look. And also, I find question part 3 is exactly the same as question 7b. So yeah, I didn't expect that. And for part B, it asks what form of energy is released in fission reactor. So the answer is the kinetic energy of the neutron produced, which we will convert into thermal energy as a moderator, so that it absorbed the thermal energy. Distinguish between solar panel and photovoltaic cell. People usually mix them up, or some people call the second one as solar cell. That's also fine, but usually people mix them up. Well, for solar panel, you can see that it's receiving radiation and turn it into thermal energy, and while the other one turn the solar energy into electrical energy. So two very specific application could be like for photovoltaic cell, is exactly what you could see from your calculator. I had an experience that there was one time the battery inside. Actually, the Casio calculator, they have two ways power. So one is, if you look at this, is two ways power. If you open the calculator out, you see inside there's a battery inside. However, if that battery runs out, still this solar cell can still help you to power up the calculator. But the thing is, you need certain amount of light energy. While for the solar panel is the one that you seldom see, because that is usually found in those rural area that they don't really have much energy network, and they need heat supply as well. So what they do is basically a very simple device that absorbs the light energy, and then they heat up the pipe which containing water inside, and these water will go down and then store in the hot water tank, and then they keep giving the warm cooler water for heat up again. So say during the night time they can have some warm water for taking shower or do some other thing, or it makes it easier to boil as well. Think about if you got some warmer water, say 60 degrees Celsius, and turn it into 100 degrees Celsius, is much more energy saving than you use in normal water, say 15 degrees Celsius, and boil it to 100 degrees Celsius. So in that way you save some energy too. Next question, these are the keywords you should have highlighted, and the part A asks you to find out the area so that the temperature of the house can be kept constant. So basically what it means is, when you say the temperature constant, is of course there must be energy loss to surrounding, but in that case the rate of losing the energy will be same rate as the energy gaining from the device solar panel over here. So that's what you are going to do, and therefore you can simply if you know this, then you can simply say the power supply must be 3.0 kW, and that would equal to this, and therefore, well, I think it's very easy to find the area, as long as you look at the unit carefully. Therefore, for part B, then you can see, I think it's very simple that you look at the efficiency 70% and also 50%. You can draw the diagram. However, I think this diagram has some problem. I copied this out from the textbook publisher, but the last one should go forward instead, as the last one should be the useful power output, and therefore it should keep going straight to the right. Question 14, a bit similar to the previous one. Basically, it is the same energy that you gain and the same energy that you transfer to the water. So PT is from the solar panel, that is calculated by these, and then the energy transferred to water will be mc delta T, which is substituted by this, and therefore you can find the area, which is unknown. Question 15 is also very similar. You have the power from the solar panel, well, sorry, the solar heater, and then the mc delta T for the energy transfer to water. Pay attention that the question has some problem. This should surely be meter square instead of meter -2, because he's talking about the area. Question 16, once again, these are the things that you should have highlighted. And for part A, it asks you the temperature of the water. So first of all, what you're gonna do is you look at the power, 400 watts per meter square. It would give you, if you got that light intensity, then it will give you the temperature up to this, which is 338 of the water. And then therefore, if you look at the power incidence of the panel, since it is 2 meters squared, then you just times 2 for the intensity and power intensity, and then for the efficiency, I think you can just read it by this. It's very simple. Once again, these are the things you should have highlighted, and similarly, you find out for 10 meter per second, and that will be the power output in kilowatts, and therefore you can calculate like below. For question 18, like what you can see from the data booklet, you need the equation for wind power, and I think, well, part A is very easy, and part B you can read the explanation here. Notice that I highlighted the keywords already. Question 19, I don't actually understand why they have a very similar question like the one you see previously in 18. But anyway, if you try to look at the how we derive this equation from the textbook in page 326, then you understand these are the assumptions, and in the actual case it's not like this. Like, imagine the air actually will not stop behind the turbine, it will keep going. So actually all the KE is not gained. Is you only obtain certain amounts, parts of the KE only, not all. Maybe that's why they do the previous question like that, because they want to reassure you that the air particles will not stop right away after the turbine. So this question is more about calculation. You can simply apply the equation, and then by substituting the V before and V after on each equation, pay attention that you cannot do like this, V2 minus V1 and then to the power of 3. You can't do that, and the reason is just because of maths. I'm not going to explain, but I guess all of you should know. In terms of maths, they are not the same. And therefore, you can find the answer at last. Question 21 is very similar to the examples. I think you can read it by yourself. Question 22, just use the equation for hydroelectric power. which is mgh over time, then you can substitute everything, you find the power. Question 23, notice the very important word deduced. So you are not expect to write this equation directly. Instead, you are going to derive the equation from mgh over time, or even E over T equal power, and then eventually you come up with the final equation like what you did in the textbook. Question 24, like what I said in the first place when I talk about the pump storage system, you can't always get the same height. So this student is wrong, because there must be some energy loss. That means the efficiency is not 100%, and therefore this claim is not correct. Question 25. Here are 4 power resources here, and these are the energy conversion between them. And you can find out the pattern. That is, eventually they are going to drive the turbine, and the turbine is to give you the electrical energy. So every single, among these 4 are ending in this way. So basically, this is what you learn in IGCSE magnetism, that chapter, talking about the generator, which means the wires coil rotate about the B field, and when they cut the B field using the Faraday law, then there will be induced current, which gives the electrical energy. So basically convert the KE into the electrical energy. If you look at some other power resources like the solar panel, or sorry, not solar panel, solar cell, then it's actually working in different way, obviously. It's actually more new technology compared to these 4. It was invented due to the discovery of photoelectric effect by Einstein in 1905, and he found out that if we shine a light ray, or more specifically the photon, on the metal surface, there will be electron come out, and these eventually help us to build the solar cell, and these also help him, Albert Einstein, to get the award of Nobel Prize in 1921. In fact, this is the only one Albert Einstein gets, and the one that we mentioned earlier, E equal mc delta d, this is not the one that he gets any prize from, not the Nobel Prize. That's the end of the video. Thanks for watching.